That's got to go backwards.
So I think everybody was kind of getting it. What I'd like to do is let class out just a little bit early, and then maybe pick up, if possible, solutions to that you worked out and how you figured it out for individual groups, so that we can record that and keep that, so that when you go back to study for tests, there's some record of not just me telling you this is the answer, but actually how you got the answer. But I think everybody found that the identity is going to be just, let's see, where did I put that pen? The identity would be just strings that go down like this, right? Because if you attach those to any braid, it doesn't change the braid at all, it just adds more rope to the braid. The next question is, what if I have a braid like this? How would I get it to be the identity? And most of you played with this kind of braid first and found quickly that you would have to reverse the crossing. And then when you attach the two, what happens is you can pick this piece up and bring it over. It's pretty neat, actually. And then I asked some of you to actually try something with more twist in it, and you came to the realization that you just reverse the crossings for whatever you're attaching to, and that becomes the inverse. So this is a group by physics proof. It's a physicist proof, right? I showed you a few examples and it works. You can see that we'll have inverses. The inverse will be the one that has the reverse crossings. The identity is this. Associativity might be a little bit more difficult to prove, but then that's the 3 check boxes of having a group. So the 2 string braids under this form of binary operation, by attaching the 2 ends together, forms a group. So I should have actually told you this, that what we were looking for is that the identity intuitively leaves things unchanged, and the inverse is what turns the object back to the identity. But I think as soon as you were playing, you got the idea with that. Okay, I want to go more into the dihedral group. It's not talked about as much in our book, but I do want to bring this example in because it's a nice example of thinking of something in a non-standard way. Non-standard examples. By that I mean examples that you've spent your whole life working with. This example is not really well done, Braid. And in fact, I think he does have the equilateral triangle, but the equilateral triangle is called D3, and I don't know if in Braid they talk about this or if I saw it somewhere, but sometimes the little subscript that you have right here, this 3, stands for the number of edges in your polygon, and sometimes that little subscript in some books stands for the number of elements in after you do your rotations and symmetrical reflections. So I'm taking the little subscript to mean the number of vertices that we're working with in the polygon. So D4 would be a square, D5 would be a pentagon, for example. So this example appears on page 79, if you want to take a look. But you're going to probably get a better treatise to this online. So I wanted to go through D3, the equilateral triangle, and form all the elements in this group. So the first is the one that leaves it unchanged. That's the one, I'm going to call that R0. Here's my equilateral triangle. I do nothing to it. It stays an equilateral triangle. Maybe you shouldn't try to copy this, then this might be hard to copy because it's going to be rotating around. I'll do this with the square, and I'll show you how to actually numerically write this out in terms of a permutation. So I think for this one you might want to watch, and if you do want to copy this later, you can copy the shapes rotating around. So another possibility is that you could take this triangle, and I labeled the vertices, and rotate it to the right clockwise once. So that's where the vertices would be if I rotated it once. I could also do it again, and I would get the vertices now have moved positions. So my original triangle, if I rotate it twice, turns out to look like this triangle on the right. This one on the right. So far, so good? Notice that rotation 2 is really rotation 1 and star rotation 1. I just did it twice. So mu1, I'm going to take the line of symmetry, draw a line, and I have in that line two exact pieces that I could fold over and they would make identical. So that's what I mean by a line of symmetry. And then I could take it and swing it. So take the entire triangle and swing it that way. So if I did that, if I just rotated around that pole, what I would get is this triangle over here. The 2 would flip to this side and the 3 would flip to this side. So I get this triangle right here. So I'm going to call that mu1 because your book calls it mu1. I could also take a symmetry line, which I didn't line up very well, but you see I could also have it going through vertice number 2, and it doesn't look nice because it doesn't look like it's perfectly flippable over that. But I could flip over that if I'd drawn it right, flip over that. This is pathetic. Even with computer-aided stuff, I can't draw it right. I know a lot of you had Dr. Nita for abstract algebra. If you ever have him for something like vector calculus, that guy can draw without computer-aided drawing. You can draw up a perfect-looking cube. Mine don't look that nice. You're going to see some cubes, I think, shortly. You're going to shudder. Okay, so we have 1 and 3 flip. Mu3, well, there's only one more vertice that I could flip over, and that's the one that goes through 3. And then 1 and 2 would flip on that reflection. So those are the 3 possible reflections I could come up with that preserves the shape of the equilateral triangle but moves around the vertices. So that's what I mean by permutation. You're really just moving around the number of the vertices.
So are we talking about 2 different groups here, one with the operation of rotation and another one with...
No, I'm going to show you the full group in a second. Okay. So what's the actual set, right? In the definition of the group, the first thing I underlined was set. The group itself is a set. Well, the set is the actual action of rotating or flipping. So each one of those movements are considered an element in the group. And I can start operating by just doing it more than once. So for example, if I did nothing to it and I did nothing to it again, I would get nothing, the same thing back. R0 would be back again. And R0, if I did nothing to it and then I rotated the triangle once, I would get the triangle rotated once. What if I took the triangle R rotated once and then rotated it twice after that? So it's rotate it once, rotate it twice, 2 more times. Back where I started, right? So my result is going to be R0. Some people are, I think it's people who play with Legos a lot when they're kids. Now they have Minecraft. And if you have kids, it's like Minecraft, it's like Legos without the mess all over the place. And now, do you know they're building these Microsoft glasses where you can make holograms and you can actually play Minecraft in your living room by moving things around? My kid said, you won't ever have to scream at us to pick up our toys again. We just have to put those glasses on and play. It's the holodeck. It's coming to life. But what you see is that people who generally do a lot of things geometrically, it's a practiced art. If you do a lot of things geometrically, you get better at it. I unfortunately had not played with Legos a lot as a child, so I sometimes need to actually take the shape and start physically moving it. Do whatever it takes to figure these things out and see them. And don't feel like that you're behind someone if you can't see those things. I always felt like I was jealous of people that could do things geometrically. Then I realized you just have to do it practice. With practice, you get it. So I would actually need to take the triangle and then see what was happening to it. Let's try another one. Let's take mu2 star mu1. So how do I do this? Well, I start with mu1 first. This is mu1. If I take my original triangle and I apply mu1 to it, I get that thing as a result. Now I take that result and I apply mu2 to that result. If I go through my original rotations, I'm going to see that my result, if I applied mu2, like if I flip over here, if I flip these two, I'm doing the walking thing. If I flip through these 2 things right here, I get this thing right here, which turns out, if I go back and look at all my pictures that I just drew on the previous slides, it turns out that that was actually R2. That was what happens when I did rotation 1, rotation 2. So that picture you get, look and compare it to that picture, the result I got from applying mu1 first and then doing mu2 to that mu1. So that tells me that mu2 star mu1 is R2. So in doing this, I can build the Cayley table. So I actually want you to try mu1 star mu2. And for that, you will need those different diagrams that I just did. So try mu1 star mu2. I just did mu2 star mu1. If you need to come back and look up on the PowerPoint, if you just want to see what something looks like, feel free. Or else recreate it on your own piece of paper. Have one person recreate it. It doesn't take that long to make the whole set of rotations and symmetries. There's a total of 6 things that can happen.
I believe
Just going right to the top here, right? And then we go over where the 2 is now, where the 2 was in the original.
and then you do, I think you
No,
do it
now
from
you
right to
apply
left.
this thing here.
Right, going through x2 to
Unless you remember
Yes.
something.
Right, right. Now, yes.
Do these get applied